Welcome back to Office Hours with Dr. Clark. Today we're looking at concentration. Oh, I don't like that color. Yes. Concentration. So that's a way to quantify solute solvents. So for example, vinegar is 5% acetic acid. So we're looking at, excuse me, 5 grams acetic acid or 100 gram solution. In a case of water, we could say 100 milliliters solution since the density of water is 1, so the grams and the milliliters are the same number. So it could work like that. But we're gonna focus on molarity. Molarity means moles per liter. So we can look at it as a formula. Molarity or M is equal to moles over liters. So for example, let's take an example here, 0.200 moles ACl and 2.00 liters. My molarity is equal to 0.200 moles over 2 liters. And that's going to be 0.100 M. So that's So we say that's a 0.1001 molar solution of hydrochloric acid. Let's look at B. So what if I had 0.200 NaOH in 500 milliliters of solution? So we have to, in this case, convert milliliters to liters. So the molarity is equal to 0.200 moles over 0.500 liters, 0.400 solution. Let's look at part C. What if I have 40.0 grams of sodium hydroxide in 2.00 liters? How would how would that, what would be the molarity and what would be the concentration? So that would be, so I need to convert 40 grams to moles. So the molar mass of some hydroxide conveniently is 40 grams. Right? So sodium is 23, oxygen is 16, hydrogen 1. So that gives us 23. So we're going to have 1.00 moles. So the molarity is equal to 1.00 mole over 2.0 liters, which would be 0.500 molar solution. And we can look at what if we want to figure out how many moles are contained in a certain molar solution. So let's take 0.250 moles, and say I have 20 milliliters. Let's say this is calcium chloride. I set up a conversion liter, 1,000 milliliter, and then I do 0.250 moles over 1 liter. So see my units are canceling. That's going to be 0.25 times 20 divided by 1,000. I'm going to pull up my calculator. I could probably do it in my head, but I don't feel like doing that in my head right now. So that's going to be 20 times 0.25 divided by 1,000. 0.005. And since it's 3 ciphers, 0, 0, calcium chloride. So it's a pretty dilute solution. Oh, excuse me. 0.005 moles present in the calcium chloride solution. Right? What if I want to figure out, okay, so what volume do I need to have a certain number of moles? So 0.150 moles. And I have, say it's a 2.00 molar solution. And let's say this is nitric acid. When we're going from molarity to mole and volume, we don't need a molar mass, right? So the identity doesn't matter with the math. The only time we need the molar mass is when we're going to grams, or we're going from grams to moles. So I take my 0.150 moles and I set up my conversion. So since I want the volume, I'm going to put liters on top, moles on the bottom. And it's going to be 0.150 divided by 2, which is, I think that's 0.0750. 0.075. And I need 3 sig figs liters, which is going to 75 milliliters. So remember, our molarity expression, just want to reiterate this. So if you see 5.00 molar, it's a pretty concentrated solution, that means 5.00 moles are contained in 1 liter. All right? So that's how we can use it as a conversion factor, much like we do molarity, molar mass, density. So let's talk about dilution. So there's an expression for dilution, M1V1, meaning M1 times V1 is equal to M2 times V2. So your M1 is your initial molarity. More concentrated. V1 is your initial volume. M2 is your final molarity, less concentrated. V2 is your final volume. So your initial volume is going to be smaller. Your final volume is going to be bigger. So in order to dilute your solution, you're decreasing the molarity, so you need to increase the volume, since molarity is equal to moles over volume. The thing about this expression, we don't need to convert our volume to liters. We can use milliliters, ounces, whatever, as long as they're consistent units. So let's take an example. So I dilute 2.50 molar ACl let me rephrase that. I dilute 50.0 milliliters of a 0.250 molar ACl solution to a volume of 100 milliliters. What is the final concentration? In other words, what's the final molarity? So this is, I'm going to use a different color here. This is M1, this is V1, this is V2. So I'm going to just set up a mathematical expression equals M2, which I don't know, times V2. And then I will solve for M2. M2 is equal to 0.250 times 50 over 100 milliliters. Do that math. That's going to give a 0.125, which makes sense because if I have 50 and I'm diluting the volume to 100, it's twice the amount. That means I'm going to cut my molarity in half. After 0.25, it's 0.125. So there are many different ways to look at dilution problems. So let's say this is, let's call this one. So we can ask this type of question. What volume of 0.250 molar ACl will I need in order to obtain 100 milliliters of 0.150 molar ACl. So the dilution exercise is so powerful because sometimes when we're in lab situations, we don't necessarily have the grams or the pure, chemicals in order to make molar solutions. Sometimes we have concentrated, what we call stock solutions, and we can just dilute them, and that will save us a lot of time and money, actually. So now let's go back to labeling. So what volume of 0.25 molar ACl will I need in order to obtain 0.150? So the M2 is always smaller than M1, so that's M2, that's M1. And that's V2, because that's in order to obtain. And then what volume is V1? That's the one we don't know. So there's always going to be one we don't know in your standard mathematical formula. So that's going to be 0.250 times V1 is equal to 0.150 times V2. Right? And our V2 is 100, actually, so we know what that is. So we can put that in, 100 milliliters. V1 is equal to 0.150 times 100 over 0.250 times 100 times 0.2 divided by 0.250. So I need 60, I'm going to make sure my sig picks up 60.0 milliliters, which makes sense. So my starting molarity is 0.25, so I'm diluting, that's always going to be the case. So I'm diluting to 0.15, which is a little, more than half of what this is. And then but I want 100 milliliters of that. So I just set it up, and so I need 60 milliliters of this concentrated 0.250. and I'm gonna add 40 milliliters of water to get to 100, and that's gonna give me my diluted 100 milliliters of 0.15 molar HCl. So different ways to look at the dilution expression. So every time we set it up, we're missing one variable. So we have to be clear to label what's the M1, what's the M2, what's the V1, V2. And remember, M1 is always greater than M2, and V1 is always less than V2. So now here comes the fun part. Stoichiometry. And molarity. Students love this so much. Because not only are we making them write formula balance equations, find moles, now we're asking them to find the moles containing the solution and solve all the stoichiometry stuff. And yeah, it's cumbersome, but it's totally doable. So let's look at an example. Let's take magnesium plus HCl. We like to use this one. Like HCl, a lot of times, is given to us in a molar solution. Give us magnesium chloride plus hydrogen gas. Let's balance this first. So if I'm given 0.100 molar, and I'm given 25.0 milliliters, the question is, and I'm also given, let's see, and I'm given 10 grams of magnesium. The question is, how many grams of H2 am I going to get? So I need to do two different stoichiometric determinations. I need to figure out what's going on with magnesium because I need to see which is a limiting reactant. So the molar mass of magnesium is 24.31 grams. So I'm going to find moles in this step. And then I'm looking at the ratio between H2 and magnesium. It's 1:1. H2. And then I'm going to multiply by the molar mass of hydrogen. And then I'm going to put all this in my calculator. And that's going to give me 0.829 grams. Okay, so now some students will write that down and say, oh, well, I'm done. But you're not because we don't know which is limiting. Is it magnesium? Is it HCl? We're about to find out. So we take our 25.0 milliliters, and then we have to convert that to liters. We can't do anything with molarity unless long as in liters. And then we look at the ratio between H2 and HCl. And then we look at the molar mass. It's the same setup, except we have to do something different with the molarity expression. So I multiply my 25 times everything in the top there, divided by, and that's going to give me 0.0252 grams. And I always like to double check just to make sure I'm doing my math, punching in my numbers okay. I'll have to make sure you're punching in your numbers okay. All right, so see, I realized I made an error. That kind of problem, like that's kind of small. It's actually 0.252, which makes more sense. So my limiting reactant is what? Is it magnesium or is it HCl? It's HCl because that gave me the smaller number of smaller amounts of product. And the theoretical yield is what? Do I add these two to get theoretical yield? Do I subtract this from the big number? No, the theoretical yield is exactly what I circled, 0.252. Remember, limiting reactant always determines your theoretical yield. That's an example of like one of the hard stoichiometric examples involving molarity. Let's take one that's maybe not as challenging, but still involves molarity. So I'm still using this equation, magnesium and HCl, to get magnesium chloride. You have to know your chemical formulas because some of these questions will be given in words. So if you see the word magnesium chloride, you need to understand that's MgCl2. If you see hydrogen gas as a product, you understand that's H2, not H. Okay. So the question is, what volume of excuse me, what volume of 0.100 molar HCl will react with excess Mg, so we're telling you that magnesium is excess, and HCl is going to be limiting, to produce 2.0 grams of H2. Okay. So we're going to start with our H2. We can't really work with grams. We have to convert to moles. 2 grams of H2, 1 mole over 2.016 grams of H2. And then we are going to figure out the ratio, which we already did. We're going to balance our equation. So we're trying to find HCl now. So we'll put 2 moles HCl on top, 1 mole H on the bottom. And then I'm given the molarity, so I'm going to use that as an expression, but I want liters, so I'll put 1L on top, 0.100 moles on the bottom. And it says what volume, right? So let's say, let me kind of make it a little more interesting. What volume in milliliters? That's typically what we measure in. Liters are huge, so we tend to measure in milliliters. So then I have to put this conversion expression. So have a nice long conversion, dimension analysis expression. But I need to make sure I double check my math. Yeah. Okay, so when I do that math, I scroll over this here, and I have a lot to write. I get 19841.2 for no space 0.2 milliliters. So you can convert that to liters. 1, 2, 3. But the question asks us for milliliters. So I look at my sig figs. I need 3 sig figs. So I'm going to say 1.98 times 10 to the fourth milliliters. And that's a lot, but it makes sense because I have a fairly dilute solution and I'm trying to produce 2 grams of hydrogen, which might not seem like a lot, but hydrogen is really tiny. So to get 2 grams of that, you need a lot of hydrogen. So, and so you always, so I always like to, anytime I get really big numbers, I always like to make sure, I did my math right. Right. You always want to check yourself. So math is good. Okay, so this is really how we use molarity as part of our stoichiometry. So the big deal comes in understanding what molarity means. If you see 0.100 N, that means there's 0.100 moles in 1 liter. So it's now a conversion factor, just like molar masses, grams per mole, density, grams per milliliter. Right? So that's really what we have to do with molarity. And if it's a limiting reactant problem where you have 2 different amounts of substances, then of reactants, then you have to figure out, like we did before in earlier video, you got to figure out how much we get from one component, how much would we get theoretically from the other component, and the smaller number is your limiting, comes from a limiting reactant, and that's your theoretical use. And then we also looked at dilution examples. And then we also talked about just how to manipulate the molarity conversion expression. All right. So hopefully this helps. This is one of the more challenging parts of stoichiometry is when we introduce molarity along with everything else you have to do to solve stoichiometric problems like chemical formula, balancing equations, figure out molar masses, using the appropriate conversions. All right. Until next time, this is Dr. Clark.